first speaker for this semester, and I'm the only speaker for today. Okay, like it was pointed out, on the website that each event could be a 50-minute talk or two half-hour talks. So, but for the first one here, this is 50 minutes. Okay, and I was told that this one has to be successful. So, so at the end of the talk, okay, don't tell me that it's a bad talk, otherwise I will kill myself. All right, so here's the topic. Okay, how is 3D graphics done using shaders? Okay, this is an introduction. Okay, eventually we will have a talk given by Dr. Scott Gordon from California on design your own game engine. Okay, so this is the important, in the sense that if you follow this talk, then it will be easier to follow this talk. Okay. All right. So overview. Okay. Modern 3D graphics programming uses a pipeline. Okay. Well, we used the pipeline before too. Only that now the pipeline is actually each stage of the pipeline of this entire process here is done by a piece of hardware. So the process of converting a 3D scene to a 2D image is broken into a series of steps. Okay, you do vertex processing, and then you do primitive processing to generate a mesh representation of the 3D object. And here, actually, you have two shaders, tessellation shaders and geometry shaders. Actually, this part here is composed of three shaders, okay? The controller and the tessellator and the evaluation, okay? But simply take this as, this tessellation shader. And then we have Rasterizer, stage, we have Fragment Shader, and finally pixels operation stage. Okay, I don't know how come that we don't get the color here. All right, all right. So we don't get that blue color. Yeah, I can tell you that this shader is programmable. Okay? So is tessellation shader, so is geometry shader, but not this stage rasterization, not the last stage pixel operation. These two stages, rasterization and pixel operations, are done by the system. We cannot change the process here. Okay. So what is a shader? What is a shader? Okay, a shader initially was, basic. It's a piece of software or computer program, okay, to compute light, darkness, color, to render a 3D scene. Okay, this term was introduced by Pixar. Okay. It's Renderman 3, okay, in 1988. So initially, shader is just a program, okay? It's just a program. But then the concept became very successful and eventually became very popular. So various shaders have been developed since. Okay, we then have Tessellation Shader, we have Fragment Shader, ultimate solve. Okay, so eventually we we have our first hardware chip, actually, pixel chip, was introduced by NVIDIA. It's 201 GeForce 3, okay? Very private, primitive, okay? But so we have a hardware that's dedicated to a special process, okay? And then gradually we have the so-called geometry shader in 209, and then we have the usual version of Tessellation Shader 2000. Eventually we have the complete version of Tessellation Shader in 2017. Okay? So today, everything is done. Everything in the graphics pipeline is done by a piece of hardware, okay? Like Vertex Shader, like Tessellation Shader. Okay? So let me briefly go through the functions of those shaders, and then I give you examples to explain how those shaders are used to generate 3D graphics in a language that you can understand. Okay. All right. So shaders, and then specialized shaders, and then pixel shader, and then geometry shader, and then tessellation shader, and like I said, that eventually today everything is actually done by a piece of hardware. And those hardware don't understand C program. They only understand a language that designed for them, the so-called GLSL or scheduling. Therefore, we need to know how to write a shader program in order to extract those shader or shaders to do things that you want it or you want them to do. All right, so here is the basic concept. Okay? Initially, 20-some years ago, okay, we have the same pipeline. Okay? We have Vertex computation. I'm sorry, not Vertex computation. You have stage to do all these things. Okay? Do model transformation, do unit transformation, Vertex lighting, projection, blah, 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 and then you do your rasterizer by yourself, okay? And then you compute your color for each pixel, and then you show your picture on screen, right? Everything is done by software. All right, and the input here is, for instance, Vertex normal color, and a function of transformation matrices, okay, such as model view matrix. Model view basically is a combination of model matrix and a view matrix. Okay. You have taken graphics, you know that first you have to do modeling, and then you have to do view transformation to convert word coordinates into viewing coordinates, blah, blah, blah. But just you have to send this information for the pipeline to do things. Okay? Now we still have to do the same thing, except that what? Some things, not some things. Everything is done by a piece of hardware here. Okay? Only that those hardware has to be given. You have to give special instructions. Instructions the hardware can understand, okay? Namely GLSL length or GLSL code. Okay? So you still have to do model transformation, view transform, vertex lighting, blah blah. Only that now the input is different. Okay? It's different, and namely that you have to give instructions using a language that the software can, the hardware can understand, okay? And this part, is simple. You have to give the instructions, but so-called uniform verbs or fragment information to a this shader. Okay? So this is what we have today, all right? For the Vertex processing stage, for the fragment processing stage here, okay? Namely, things that we have to do by ourselves now are done by the hardware. So Vertex Shader replaces what? Replaces these operations, Vertex transformations, normal transformation, normalization or computing Vertex lighting. Okay? Computing Vertex lighting is that you set up the environment, but you don't do the computation yet. That computation is actually done by the last two stages. Okay? So, and of course that likewise, this stage here takes over things such as color computation, texturing, color blending, etc. All right. So briefly, what is each of these special hardware? Well, this is not actually special hardware. It's just a special computing unit of the graphics card or the video card dedicated for special purpose. Okay? So, but we can simply just call those hardware like Vertex Shader, Tessellation Shader, okay, or geometry shader. When you do 3D graphics, you use a mesh-based modeling and rendering process, meaning that for each 3D object, you have to get a mesh representation of that object. And if necessary, then you have to code that 3D representation with a texture or something else, okay, bombs, etc. I explained all of this. Okay, so tessellation, you know what a Vertex Shader will do. Now, tessellation basically is to generate a mesh representation based on the vertices that are provided to a Vertex Shader. Okay, so basically, generate a large number of triangles to form a mesh representation of a given 3D object or object in your 3D scene. Okay, so intuitively, tessellation shaders build a mesh representation, okay? Triangle mesh. Okay? And geometry shader lets you do anything, lets you manipulate those faces or triangles of the mesh. Okay? So you can alter those triangles, you can even delete some of the triangles, you can generate additional primitives, okay? Such as this case here. Okay? So this is the original 3D model. You can, first you have to generate a mesh representation for this torus, and then for each triangle here, you can do some editing to create or to generate additional primitives. Okay? And Rasterizer is the process to convert each triangle. Okay? At this point, you have geometric information on the vertices. You have topological information on the on the mesh. Topological information is that you know, okay, these two vertices is connected by an edge, and these three edges will form, a face or triangle. Okay, but you don't know which pixels on the screen should be excited in order to show those edges, in order to show the interior of the triangle on the screen. And so eventually you will see the desired, image on screen. Okay? So Rasterizer does the first thing. Find out which pixels should be excited on screen to represent those edges. and also which pixels on screen should be excited to represent the interior of those triangles, or for the measure representation of the given object or the given 3D set. Okay, so rasterizer is basically just a process to find out which pixels on screen should be excited or should be identified as the edges of the triangles and the pixels, that should be identified as the interior of those triangles. Okay, so this is what the rasterizer stage will do. Remember that this stage is not programmable. Okay, you cannot do anything to this stage, right? Let's accept the result here. Okay, so basically, first, you have the information on the vertices, such as location, such as texture, value that you can use for those vertices, but you don't know which pixels should be used or should be excited on the screen to have this page displayed on the screen. So that's the job, the first job of the rasterizer, okay? To identify or to generate the edges of those triangles, okay? And then to identify the interior pixels that should be excited to show the interior of those triangles, okay? So these are the two jobs that the rasterizer will do, okay? And if you only do the first step, of course, you only get the edges of those triangles, okay? If you do also the second step, then you will also get the interior, okay? Interior pixels render straight. Okay? Here we didn't use different intensity, so just to show you that. Okay? In addition to the wireframe drawing, you also get all the interior pixels identified and excited. Okay? All right. So. In the fragment shader, at this point, we know which pixels should be excited. But how? How is what color or what intensity values or what kind of texture information should be used for those pixels. Okay, so this is the job of the so-called fragment shader. Okay, to assign colors to the rasterized pixels, basically those pixels, like representing the edges and also the interior of the triangle. Okay, again, then you have to this stage here is programmable. Therefore, you can send GLSL code or instructions to the shader to do things such as just simply set all the pixels to red, or do this, do that, or check how those texture information should be combined, etc. Okay, so this is what the fragment shader will do, and the pixel operation stage. This stage is not programmable either. Okay, here basically it determines for each pixel. Now each pixel could be the projection of 2 points on the given object or several points in your 3D scene. So you have to determine which points, intensity or color should be used to paint that particular pixel. So this is the main job of pixel operation, the pixel operation stage here. Okay, you don't have control of this part. All right, so you know basically what each of these stages will do, and then we'll see how. Well, basically, this is what pixel operation stage will do. Okay. several points are projected to the same pixel, then which points intensity or color should be used to paint this pixel here. When we do the projection, process, okay, each 3D point will be projected to a 2D point on the image plane, but we also keep a depth value for that point. Therefore, for this pixel here, now you have 3 points. Okay? And we also have 3 depths, okay, for this one for each point. Therefore, the system can compare those depth values to see which point is closest to the viewer. Therefore, this point is visible to the viewer. Therefore, we use intensity or color of this pixel and the title for this point here and this pixel. So this is what the pixel operation stage will do. Okay, so let's see how all of these things are done. It's in a very simple manner. Remember, I said I use language that you understand. So this is a very simple example. Okay, so the purpose here, or the goal here, is to use world map to what? Texture or to paint a sphere. Okay, so, or simply we use a world map to texture a sphere. Okay. So how is this done? How can we do this thing using those shaders, right? So here are the things that we need to handle or to know how to use the shaders to handle these things. Okay? So remember that, we need, for each object, we need to build a mesh representation. Okay? We can provide vertices of the mesh, but the system needs to know on the hardware, tessellation shaders need to know how triangles should be performed. Okay? Before. Okay? And how should each mesh element be recorded? So inside and outside of each triangle can easily be distinguished. We record triangle here, okay? It's tricky, okay? The normal of the triangle should be able to tell that this is a triangle facing this direction or that direction. This direction could be, a visible triangle, meaning that the user can see the triangle. This direction could mean that the triangle is not visible, meaning that the user would not be able to see the triangle. Okay? So that information should be clear. You shouldn't make any mistake. Okay? And how to load the representation into our scene. Okay? So that the stage or the shader would know what to do with those representations, what to do with each stage here, and how to ensure pixel operations perform properly. So in the service I unique, correct. Okay. Things that you are not supposed to see shouldn't be showing on screen. Only things that you are supposed to see will be showing on screen. All right? Remember, that's the job of the last stage, pixel operation stage. Okay? So, first thing, Vertex Shader. Since Vertex Shader needs to know to do. So first, we have to provide a bunch of vertices to the Vertex Shader. What vertices? You need to let the shaders know how the sphere will be represented. Therefore, how should information from the world map be put into that state, all right? So what we'll do is we will cut the sphere into slices. Okay? For instance, you cut the sphere into 4 slices. Okay? And each slice here has 2 circumferences. Okay? And each circumference, of course, has different radius. Okay? and how to put vertices on those slides, okay? Or how to subdivide the circumference of each slide into a certain number of points, and how to group those vertices into triangles, how to select texture coordinate, okay, depending on the nature of the texture material, the world map, okay, and how to generate normal vectors for each vertex, so we can do lighting, so we will be able to eventually find out what color, what intensity should be used for that pixel. You might not be able to get, texture for each point, for each pixel. Therefore, you have to do interpolation, either linear interpolation or bilinear interpolation, to get an approximation for that information. Okay? So the concept is, okay, given a sphere, I divide it into many slides. Okay? So let's assume that we divide the sphere into 48 slides. Okay? And for each circumference, we put 48 uniform points on that circumference. Okay? The reason we use 48 is, first of all, 48 is big enough, not dense enough. And secondly is that in order to compute vertices, okay, we need to rotate the circumference, okay, by 1 degree, 360 divided by 48. So you could use 50, you could use 48, you could use 55. But dividing 360 by 48 will give us a better value to do the rotation. So that's why we use 48, okay? And the Vertex Shader needs to know what? Where are the vertices of the mesh? How to compute those vertices? How to perform vertex normal transformations, okay? How to compute texture coordinates? How to interpret the textural coordinates through the Rasterizer to the fragment head, okay? So you have to tell the Vertex Shader explicitly where are those vertices in a language that we can understand. So basically, you have to send GLSL instructions or GLSL code to the shader to provide this information here, such as we divide this into 48 slides and 48 points for each slide, and we need to tell the next stage how to form triangles. Okay, how to form triangles. This work should be given in a way so that the tessellation shaders can do their jobs easily and correct. And importantly, the vertices should be recorded in a way so that inside-outside information will be easily to identify. Okay, and you also have to tell the system or the Vertex Shader, okay, how to get the texture information on the given world map, right? And same thing. Okay? You just divide this into 48 slides, okay? And for each slide, you put 48 points, okay, into that slide, okay? And then, of course, this point should be correspond to the corresponding point on your sphere, etc., etc. So this information has to be given to the Vertex Shader, okay, to tell the shader how information from the world map be provided, okay, so that for each reference here, I get a piece of information from world map. From world map, basically, we call it a text. We also have to compute a normal vector for each point of this mesh here, for each vertex of this mesh here. All this information has to be provided to the Vertex Shader, right? And remember that we have to provide information in a way so that the shader or shaders can do their job job easy. Okay, so we put the vertices into a vertex array. Okay, slice by slice, right? But we don't want to duplicate this information too many times. So we use indices to represent each triangle. Okay? So we have to let the shader know for this triangle here, where it should go to get the vertices of the triangle in the vertex array. We use indices. Okay? So you also have to build what? You also have to build an index array here. Okay? For each vertex here, actually you have to provide information such as geometric transformation, texture information, lighting information for each vertex here. So this is not just a vertex. This is a bond, a set of or a group of data here, all right? That you use index into this vertex array here to get the information you need. Okay? So this information will be provided to the next stage, Tessellation Shader. Okay? Tessellation Shader. Okay. Again, in a language the shaders can understand. So it must be a GLSL code, a program. Okay? And that program has to be compiled, okay, separately, because they don't understand in C++ cannot, cannot communicate with shaders directly. Okay. Those GLSL code have to be, a program has to be compiled and linked, okay, and then loaded into the shader. Okay. All right. So remember that the tessellation shaders are to form triangles. So you have to tell the shaders how each triangle is formed using indices. So for instance, you form this triangle here using this vertex, and this vertex. You find this vertex, this vertex in this entry of your vertex array. You find this vertex in this entry of your vertex array, and you find this entry in this entry of the vertex array. Okay? Therefore, the tessellation shaders can build a mesh for the given sphere. Okay? For the given sphere. Okay? But at this point, you only have topological information. At this point, you know that you must build an edge in this vertex and this vertex. But you don't know any information for geometry information for this edge here. Okay, so you only have topological information. That's why we need the next stage, rasterization. Okay, so after the so-called tessellation stage, you will have what? A mesh representation of the sphere. Okay, the mesh is formed by a bunch of triangles. Okay, a bunch of triangles. We know how each triangle is formed because we know the indices of these triangles, and we know how to use the indices into the vertex array to find the location of those vertices. Okay, but that's all we have for now. Okay, so the next stage is to, well, I'm sorry, that we have a stage here called geometry shading. For this particular example here, we don't really need this shading here, okay? But this shader here is actually very important shader, especially for game design. Okay? You will know why. All right, this shader here, okay, the so-called geometry, can aid the mesh formed by the previous state. So this shader gets its input from the output of the tessellation shaders, a mesh representation. Okay? In this case, a mesh representation of a sphere. All right? So for this stage here, you can delete some of the triangles from the representation, from the mesh representation. Say, you don't want this triangle or this triangle included in the mesh, in the rendered result file. Ignore this triangle, ignore this triangle here, okay? And you can also add additional primitives. Okay? Additional primitives can be generated, such as you put a new triangle on this triangle. So you put 3 new triangles on this triangle. We didn't do this thing here, but this is a possible function for the geometry shader. All right, and actually, geometry shader can do a lot of things. Okay, and like I said, it can generate many interesting visual effects. Okay, for instance, generate additional primitives. We saw this example right earlier. Okay, or you could generate, using put a bounce on the on an object. Okay, so this is a sphere. Okay, you can get this kind of visual effect. All right, you would assume that this sphere has bounce, but actually the underlying surface of this thing here is exactly the same as this sphere. We didn't change the geometry of this object. Okay. However, we are able to generate a visual effect like this by what? By manipulating normals of the surface. Okay. So if this is the direction of the normal of the surface at this point, I can change it to this direction. Therefore, in that case, you get different visual effect. Okay? So this is one of the things that geometry shader can do. You don't change the underlying representation, and yet you could generate various virtual visual effects. Okay? Such as this one here. Or you can
Fuhua, may I ask a stupid question perhaps? Okay, so this case of the red ball, there is also a shade. The shade is a perfect ellipsis.
The shadow here is actually the shadow of the sphere, of this sphere.
Yeah, that shows that you didn't change the geometry.
Right. The geometry, the underlying geometry is actually this sphere. But by changing directions of the normal vectors at many different points, I could generate different visual effect, different intensity values. Okay, that would show, for instance, a bomb. Okay, or like this case here, this is a technique used in game design. Okay? This is a warrior, right? This is the original surface representation of that warrior. Okay? But you can get this kind of visual effect. Okay? And you get bombs, and then you get scales here. But you didn't change the geometry. A shader didn't change the underlying shape. It simply manipulates the normal vectors or puts new primitives on new triangles, small triangles on existing triangle to create the visual effect of a bomb or a scale, essentially. Okay, this is a very common technique used in game design. Okay, we didn't use this property or functions of geometry shader here because our job basically is just to put a world map on the sphere. Okay, we don't need to generate the bombs or to generate scales. But you need to know that these are the functions a geometry shader can do or can perform. Okay? So that's why I said geometry shaders is important. Okay? Important in what sense? Important generate things, okay, on screen without actually changing the underlying representation of the object. Okay? So in order to be a good, game designer, you need to know how to use this kind of function. All right? And then rasterization. Okay? At this point, you only have topological representation of triangles. You know where the vertices are. You know which vertices should be connected, using edges. But you don't know how pixels on screen should be rendered in order to generate, to show an edge between that two vertices, or in order to show the interior of a triangle, or to show necessary information that would represent the interior of a triangle. Okay, you have to. The system needs to know how to do this. So you will do the so-called rasterization stage, okay, to actually identify all the pixels that should be identified, that should be rendered, okay, in order to really to show an edge on screen, or really to show a triangle on screen. So that's the purpose of this stage here, to really to actually identify those pixels that should be rendered to represent edges and to represent the interior of triangles on screen. Okay? We don't have no control for this part, because this stage is not programmable. All right? But you need to know the function of this stage here, rasterization, okay, to identify pixels on the edges of triangles and the interior of those triangles. Okay? So this is the first stage, to identify pixels, to represent the edges of the triangles, and then also identify all the interior pixels. Okay? So after this stage here, if the second stage is not performed, you will get all the edges of the triangle. All the edges of the triangle displayed on the screen. All right? And then you have to really compute the intensity values or colors of those pixels. Those pixels identified in the previous stage. Okay? And this is the job of the so-called Fragment Shader. All right? Fragment Shader. Okay? So this stage is programmable. Okay? We can control this stage, okay, by sending GLSL instruction or GLSL code to the shader. Okay? All right? So basically, we know the information for all the pixels provided to the Vertex Shader. We know the location. We know the texture or texels that should be used for each pixel here. Okay? But how about pixels lying on this page here, or this page, and also all these pixels for each state line, or for each interior pixel. So this is the job of the so-called Fragment Shader. Compute the color or intensity values for those pixels. So first, for this line here, or for this horizontal line here, okay, you need to know what the values should be used for pixel A and what values should be used for pixel B. So Fragment Shader will do this by interpolating colors or texture values of these two pixels to get a value for A. And do the same thing for B, all right? Once we have the values for A and B, then again we can use interpolation to find what. For instance, for C here, what is the color, what is the texture value that we should use for this interior pixel here, all right? Of course, for all the interior pixels, okay? This is again done using interpolation, okay? Technique is simple, but you need to know how instruct. Okay? Now you can just tell the shader, don't do this. Paint every pixel in red, or paint every pixel pixel in blue, blah, blah, blah. You have the power, okay? But of course, you don't want to do that for this example here. You want to calculate it, the texture value for each pixel on the boundary and for each interior pixel here. All right? And then once this is done, then you go to then the process moves to the next last stage, pixel operation. Okay? This stage is not programmable. Okay? The system will do this work itself completely. Okay? Basically, intuitively, this stage is to determine for each pixel here what information should exactly be used. If several, like in this case, if 2 points are projected into this pixel here, then which points information should be used for this pixel? Should D1's information be used for this pixel, or D2's information be used for this pixel, all right? So that's the job of the so-called pixel operation, okay? We can use several techniques for this work. We can use Z-bar method, we can use spin-line method, we can use depth source method, we can use, what's the name of the trick? Sorry, don't have enough energy. But anyway, that Z-buffer method is used because Z-buffer method is hardware friendly. Okay? It's very easy to implement. Okay? So that's why this stage uses Z-buffer method to determine which information should be used for each pixel here. Okay? Therefore, when all this information put together, you would be able to see what? A sphere with the world map texture on it, okay? Correct, like this one. So output of this program here is precision of 48 slices, okay, of the sphere, and for each slice we have 48 points, all right? So this is what you would get at the end for this simple program here, or for this simple example here. So now you understand how a simple 3D graphics example is done using shaders. Of course, I didn't show you the code, okay? You have to take CS535 to learn how to do a shader program, okay? Remember, learn that in CS535. All right, so this is how we do 3D graphics using shaders. All right, so this is a process using shaders to model a sphere, and the texture, the sphere with a world map. Okay. I hope that I have given you, a picture of the whole thing using this very simple example here. A sphere is a world map. To texture the world is a sphere with a world map. Okay? Remember, the only difference is 20 years, 30 years ago, we do everything using software. These days, everything is done by hardware. But you need to know how to instruct the hardware to do the right thing for you using GLSL code. And this GLSL code has to be compiled and linked to the shaders, okay, by your C++ OpenGL code. Any questions? Oh.
How does the pixel shader go about rendering semi-transparent textures?
Well, if that's the case, then if this pixel here is transparent, say 80%, then you don't completely ignore D2 here. The computer intensity of this pixel 20% of the information you get from D1, and then 80% information from D2. If this part is transparent. Of course, you need to know the degree of transparency of this part. But this information, of course, will be provided to the shader. So the shader will know how to do the computation. Yes?
When we are modeling different points, you said we use triangles.
Yeah.
Is there any reason why we use triangles and not other shapes?
There's only one reason. Okay? It's easier to rasterize a triangle than a general polygon. Okay? For a triangle, for each scan line, you only have 2 intersection points. For general polygon, you could have 4, 6, 7, 8. Of course, number of intersection points is also always even. But for a triangle, you always just get 2 intersection points. Okay? Those 2 intersection points could be the same, but just 2 intersections. So the reason is very simple. Easier to rasterize or scan convert the triangle. That's why they choose, triangle mesh to represent 3D objects. And the rasterization state is designed only for triangle. It cannot handle anything else. Well, also edges. Anything else?
But on that example that you showed, you only created a sphere mesh and then textured it. You did not shade it, right?
Actually, you should, for this example here, shaded information, lighting information is also input at the first stage. Otherwise, you wouldn't see this. Otherwise, you would see a dark space.
Thank you very much.